We are now at the waterfront of Kaust, where we have a healthy mangrove ecosystem. This mangrove here sequesters about 5 times more carbon per hectare than the pristine Amazonian forest does. And as the mangrove traps carbon, it raises the seafloor at rates of about 3 to 4 millimeters per year. So they play an important role both in mitigating climate change by removing carbon dioxide, but also they play an important role in defending the shore.
مع مواجهة محيطاتنا للتطفل البشري والتغير المناخي، هناك علماء يسهرون الليالي بحثاً عن حلول لهذه المشكلات، مسلحين بالمعرفة والخبرة والشغف والأمل، ومدعومين من قبل مؤسسة تؤمن بمسؤولية العلماء في إنقاذ كوكبنا.
So we all know that oceans face many challenges, and those challenges are linked to climate change. So one of the things that is happening to oceans is that they're acidifying over time. We also know that the pressure of people, what we pump into the oceans, it leads to degradation through what we take out of the oceans. So it's very important that, again, we think collectively how to address the issues that oceans are facing.
أحد تلك المحيطات هو البحر الأحمر، حيث تقع كاوست، وحيث يستخدمها العلماء كمختبر لهم.
We take cylinders of soil from the mangrove, and then we look at the emissions of carbon dioxide and methane from the sediment core. And then we also look at the carbon stock that has been accumulated in the mangrove, and we discover one more mechanism by which mangroves contribute to remove carbon dioxide, that is through the dissolution of carbonates. And that process releases salts that is called alkalinity, that shift the chemical equilibrium of seawater in a way that it's able to suck more carbon dioxide. And we found that that mechanism of alkalinity generation by mangroves enhances their carbon removal capacity by a factor of 20 times. So these are really the most important sinks of carbon in the biosphere. Because we were not aware of those values, the mangroves have been destroyed for decades. And over the last 50 years, we've lost about half of the global extent of mangroves. And since we realized of their important role in carbon sequestration, now there's a new concept called blue carbon, which I actually helped develop. And that concept refers to the capacity of mitigating climate change through the conservation and restoration of mangroves. So for the first time in the last decade, mangroves are no longer declining, but they are steady state, and they're starting to increase in many areas of the world. For instance, in the Red Sea, they have expanded by 13%.
The Red Sea is a very interesting ocean. It's called a sea, but it has the features of an ocean in terms of its geology and how it's forming. It's also an ocean that is very saline, and it's also an ocean that has very high temperatures, particularly at deep water temperatures. So the temperatures here are maybe 10 degrees higher than in many other oceans for the similar depth. That means that the species that have evolved in the Red Sea have evolved to deal with those conditions. And that makes it a fascinating place to discover corals that are very resilient because they had to adapt already to high temperatures and salinity. If we think about how to sustainably use the oceans for food, again, understanding the species that are present here may give us insight into what species could be farmed effectively in other parts of the world as the climate change starts to increase the ocean temperatures.
The Red Sea is a long basin, and it is subject to two different atmospheric systems from top. One from the southern Red Sea, one from the northern Red Sea. The northern Red Sea in the winter brings some fresh air, and this fresh air cools the northern Red Sea, quite colder than the southern Red Sea. Now this fresh air makes the surface water in the Red Sea cold. It becomes heavy, and when it becomes heavy, it sinks. And during some events where there is an extreme cold temperature coming from the eastern Mediterranean, from the north, the water becomes so cold that it can sink all the way down along the bottom of the Red Sea, bringing oxygen from the top. First, it ventilates all the deep waters, and it changed the whole physiognomy, and it ventilates the whole Red Sea in a matter of 10 years. We used to think it takes 70 years. Snapshot of the Red Sea, you only see some kind of mesoscale, what we call vorticities, like eddies, circular movements. And these circular movements, depending on how they turn, they can bring nutrients from down deep all the way up. As they can spread the nutrients towards the coral reefs. So this is one mechanism where there's general circulations can explain how the nutrients are being spread and bringing the nutrients for the chlorophyll to grow and bring food to the fishes. I'll give you an example. In the Southern Red Sea in the summer, we see chlorophyll blooms. And chlorophyll blooms are very important because this is basically the base of the food chain in the sea. So understanding the blooms and what's driving them is very important, obviously. And in the south, they happen in the summer. We see them from satellite data, and which is not standard in the summer in a tropical sea to see chlorophyll blooms in the summer. And what we show is that there is intrusion of cold water coming from the Indian Ocean that brings nutrients to the Southern Red Sea that creates the blooms we're seeing. So any impact on this circulation might impact on the productivity of the whole Southern Red Sea. And it will have a great implication in terms for fisheries, for corals. Understanding all this functioning of the system allow us to expect what's going to happen in case of changes in the conditions.
إلى جانب قوى الحوسبة الفائقة وصور القمر الاصطناعي والاستشعار بالطائرات التي تساعد إبراهيم وفريقه على فهم البحر الأحمر، يوفر عالم زميل وصولاً أعمق إلى البحر الأحمر عن طريق ما يسميه إنترنت الأشياء تحت المياه.
In underwater, until today, we're still very much using acoustic, meaning the sound method for sending signal or data. But in our case, we try to go for a few tens of thousands of times faster than the acoustic method. And also the other advantage is we want to make the oceans silent and create as little disturbance to the sea mammal as possible. This is the high vacuum equipment that allow us to do material growth layer by layer, atoms by atoms, so that we'll be able to build it into the device structures for our optoelectronic or photonics components such as semiconductor laser or high-speed photodetector. That is the receiver that we eventually integrate onto sensor or communications system, such as this one that we are making is the very high-speed visible light communication, or we call it as Wi-Fi, light-based communications, by using light to send very, very high data rates for internet access, for example, and for data communications. The system that we are building hopefully one day will replace the slightly lower speed Wi-Fi that we're using for our mobile or portable devices. There are a couple of other competing technology as well. For other research groups, they usually would use LED, or the so-called light-emitting diode. Using LED, you'll be able to get up to a few tens of times faster than Wi-Fi. But in our case, we are among the very early group to adopt laser-based Wi-Fi. So in our case, we always go beyond so-called gigabit per second.
يبدو هذا واعداً جداً، لكننا ما زلنا نريد أن نعرف كيف يساعد البحر الأحمر في العثور على حلول للمساعدة في إنقاذ المحيطات.
The Red Sea is a very interesting system in a global picture because it's already a very hot and very salty environment. And in many ways, the Red Sea looks like what we think most of the world's oceans will look like in the next decades to come. So in a way, it's a kind of a living laboratory that we can experiment in and understand that process right now. Most marine organisms release eggs and sperm into the water, and these are carried away by currents. And this phase of life is also extremely difficult to study because of the number of eggs that are released in the wild. And so if we can study model systems for larval dispersal in aquaria, we hope that we can learn some general concepts that can be applied and understood in many other species. This element of movement is absolutely critical if you are trying to design marine protected areas that are going to work. Because if you protect one area, you need the offspring from those organisms to travel and connect to other areas as well. This study of connectivity has been very difficult to do in the wild and actually in the field. And much of what we have learned has been conducted in aquaria.
لا تحوي الأحواض الأسماك وحسب، بل الشعاب المرجانية الرائعة أيضاً، التي تمثل أساساً في نجاة هذه الأنظمة البيئية تحت المائية.
Coral reefs cover less than 0.1% of the surface area of the ocean floor. That's really not a lot. It's really, really small. But now imagine that this small area supports 30% of all marine life. We're basically concentrating most of the species that we have in the ocean in these hotspots of biodiversity. So they're not just beautiful environments. They're not just colorful and charismatic. They're actually essential for our oceans and for us, because more than 500 million people on this planet rely on coral reefs for their livelihood. They provide food on the table of these people. I think it's fair to assume that the news for coral reefs are not good. Right now, the projections are that by the end of this century, more than 90% of our coral reefs will experience bleaching every single year. This is something that they will not be able to survive. We already saw what the 2 consecutive bleaching events did to the Great Barrier Reef.
لكن ما هو الابيضاد؟
So if we look at corals, they're actually animals. It's an animal that builds a skeleton underneath. Within the tissue of the animal, you have small algae. And it's a symbiosis where you have a host coral host algae symbiont relationship. The algae is able to harvest light and transfer it into energy. And so the coral benefits from the energy provided by the algae and helps to somewhat farm the algae in the tissue. But if we have high temperatures, this relationship that is mutually beneficial at normal temperatures breaks, and therefore the symbiosis breaks. And what happens is the coral starts to not benefit from the algae anymore and expels it. So the coral will then turn white because the algae is what gives it a lot of its color, and it can sustain in the state of what's called bleaching, a bleached coral, for some time. And if these conditions, what we then call degree heating weeks, persist, where we have temperatures above the mean maxima, what the corals usually experience, we really see often huge mortalities associated to this, and corals that then get degraded in a single marine heat wave event to large scale.
But if we manage to really help them create new populations, and we have shown recently that this can be done in just 1 generation or 2, by just picking parents from the right locations with the right adaptations in a single generation, we can increase the resilience by several degrees, and this translates to decades. The Red Sea environment, as Sebastian already said, is ideal for us. We're looking at an ocean that has both one of the hottest environments for corals as well as one of the coldest, because it spans almost 2,000 kilometers from north to south. We have a very hot south, we have a very cold north, and this basically means that the corals in the north will have a much more benign environment for the coming decades than most corals elsewhere in the world. Now this for us allows us to see, can we use the corals from the hot south and already cross them with the corals from the cooler north to produce populations in the north that have temperature resilience for temperature that we would expect by the end of this century or maybe beyond, which is much longer than what we actually project for most corals elsewhere. It is basically an ideal test bed, a life experiment ongoing that we can use to test our technologies and our approaches, and then hopefully start doing the same things in other parts of the world.
So at the moment, the problem with coral restoration is that coral restoration is among the most expensive. And that's simply because you need dive time, you need to be able to anchor the corals underwater, and it is very, very expensive. One of the ways to reduce cost to some degree is to have these land-based facilities, because here we have easy access to the coral. We can really ensure that the corals have the best environment, and then we can take these out and restore the local habitats with them.
Unfortunately, coral really don't make it easy for us. So they're not just quite complicated to maintain. They rely on these complicated aquarium systems. But on top of that, they only reproduce a single time in the year. So if you want to do any research with coral larvae, you have one shot a year, and then you have to wait again. Now, in order to counter this, we teamed up with our collaborators from the University of Derby and a company building aquarium systems. And this is what we came up with. This is what we call a coral spawning system, where each tank is controlled individually for temperature, light, and moonlight cycle. If you are a species that relies on spawning a single time in the year and just releasing your gametes, you need to make sure that all the individuals do it at the same time. And to synchronize this, corals use temperature and the lunar phases. So the full moon is the trigger that tells the corals on what day they should release their gametes so that they can all release them at the same time and mix. With these systems, we can control all of these parameters and basically make them spawn when we want. And because we have so many different systems, we can have every system spawn at a different time in the year. So instead of just relying on a single spawning, with this setup, we can hopefully have 12 to 24 spawnings every year that give us larvae to the research.
بالإضافة إلى البحث المقام في الحرم، هناك القرية المرجانية الحيوية الجديدة، حيث يقوم العلماء البحريون بمشاركة ومقارنة تجاربهم واكتشافاتهم.
I'm very excited to be here today, and we are officially opening the Coral Probiotics Village.
That's a pretty important project for us that Raquel Peixoto kind of federated us to do with her.
It's a very special place where we found the perfect conditions for us to establish this natural laboratory where we are testing some very innovative approaches to protect corals from bleaching and other threats. We will be inoculating probiotics on some of these worms to try to boost their resilience.
She's found a really nice spot, and she's created the idea of bringing everybody together in a specific area and basically bundle all the research at this one point. And I think over time, this will have huge benefits because there will be lots of synergies between the different research projects. She on the probiotics. We would like to place our maritaxia technologies in a neighborhood of this village where we can do then selective breeding and work on adaptation. Where we genotype most colonies, we can basically follow them and track them over time and see how the ecosystem, not just single colonies, respond to all the things that we're working on in the future.
We have several objectives. We have lots of experiments going on. In one case, we want to see if inoculating probiotics before the bleaching event make the corals stronger and mitigate bleaching or avoid bleaching. We also want to see if, in case they bleach, they recover faster or they don't die because of the probiotic. In some other cases, we started with bleached corals. And then in this case, we want to see if we can revert the process, if we can save the bleached ones compared to the other ones that are not inoculated. The Red Sea, in my opinion, hosts the most powerful probiotics in the world, and we inoculated our probiotics from these corals in the Red Sea because they've been exposed to higher temperatures and tough conditions for so many years that we believe that the microbiome living within them have also evolved in a way that we can learn from, apply here, and also export this to other reefs in the world, at least the knowledge and the mechanisms that make them stronger. And Professor Berubin is also looking at the fish and how they respond, if we can attract more fish, if they are healthier or not, if there's any impact. So right now I expect to see some of these results coming out, and Professor Aranda will help me with the things that are living within the corals, the symbionts, the bacteria, and so we hope to see improvements.
it's a huge step to go out of the lab into this scale
Exactly.
in the field, because I think otherwise we'll never know how much we can keep going and how scalable the whole thing is.
There are no model species that are targeted for inoculation, but of course they don't live in a tank, they live in a real reef, and that's the advantage because you can then follow what the other benthos does around those sites of inoculation. So we can compare how things survive or strive or settle. And it's not just about corals, there's also a lot of macroalgae there and sponges, so those are really important components for example, the carbonate cycle of the reef, especially Halimeda, which is a big carbonate producer, and so we were also interested in the broader benthos in this sense.
Time is of the essence, I think, because we've been having bleaching events every year or every other year. So corals don't have enough time to recover, even in resilient ecosystems and areas, just like we have here in the Red Sea. And I think because of that, these corals don't have time to recover. So it means we really need to start doing something right now.
At the end of the day, the only thing that will secure the future is reducing our carbon footprint. But we're already committed to a temperature increase that will put these ecosystems under a lot of stress, maybe even beyond the point of breaking. And if we lose them, they will be gone. I don't believe that corals will go extinct, but that's not important to us. What is important to us is the ecosystems they build and the services they provide, because this is what puts food on the table for millions and millions of people on this planet.
تسبب نمو تعداد سكان العالم بازدياد انعدام الأمن الغذائي والمائي. أيستطيع علماء كاوست العثور على الحلول المستدامة المطلوبة لإطعام العالم؟ انتظرونا في الحلقة القادمة لمعرفة ذلك.